Welcome. There is nothing to do now but rest. Let your breath find its own slow rhythm, and let your body sink a little deeper into whatever is holding it. Tonight, we drift toward something vast and dark and strangely peaceful, the black hole. Not to fear it, but to wonder at it, gently, until your eyes grow heavy and sleep arrives on its own. Massive stars end their lives by collapsing inward on themselves. When a star many times heavier than our Sun runs out of fuel, its core can no longer hold against gravity's pull. The outer layers may burst outward in a supernova, while the core keeps falling inward, smaller and smaller, until it becomes something new. This is how many black holes begin their quiet, dark existence. Every black hole has a boundary called the event horizon. It is not a solid surface, but a point of no return, an invisible line drawn by gravity itself. Beyond it, space-time folds so steeply that nothing can find its way back out. Astronomers describe it as the edge of darkness, though it holds no texture, no wall, only a threshold. Nothing that crosses the event horizon can ever come back, not even light. Photons themselves, the fastest travelers in the universe, cannot escape once they pass that boundary. This is why black holes appear utterly black against the sky. Light bends toward them, circles them, and disappears, leaving only darkness where something enormous quietly resides. Black holes were first predicted by Einstein's general relativity, long before anyone saw one. In the early 1900s, physicist Karl Schwarzschild found a solution to Einstein's equations describing a point where gravity would become infinite. At the time, it seemed like mathematics alone, an elegant curiosity. Decades later, the universe revealed it was real. The first direct image of a black hole was captured in 2019. A worldwide network of telescopes working together as one instrument gathered light from a galaxy 55 million light-years away. The resulting picture showed a glowing ring around a dark center, exactly as theory had long predicted. It was a quiet triumph, decades in the making. Stellar mass black holes typically range from 5 to 20 times the mass of our Sun. They are the smaller cousins in this cosmic family, formed from the collapse of large stars. Though modest in size compared to their supermassive relatives, they still bend space profoundly around them. A single one could hold the weight of many suns within a region smaller than a city. At the center of our own galaxy sleeps a giant named Sagittarius, a star. It holds the mass of about 4 million suns, gathered into a space no larger than our solar system. Stars near the galactic core swing around it in tight, graceful orbits, tracing paths that helped astronomers finally measure its weight. Light from those orbiting stars has let us watch, decade after decade, a slow dance around something we cannot see directly. Every galaxy, it appears, cradles such a giant at its heart, quiet and unmoving, while everything else turns around it. Spin is a property black holes carry, as real and measurable as mass. Like planets and stars, a black hole can rotate around its own axis, sometimes at astonishing speed. Astronomers infer this spin by studying how it warps the light and matter swirling nearby. A rapidly spinning black hole drags the very fabric of space along with it, a phenomenon called frame dragging. 3 simple numbers are enough to describe any black hole completely: its mass, its spin, and its electric charge. Physicists call this the no-hair theorem, meaning black holes hide every other detail of what fell into them. A black hole made from a collapsed star and one made from a cloud of gas would look identical if those 3 numbers matched. In a universe of endless complexity, there is something almost restful about an object so simply defined. Let your breath find its own rhythm now, without any effort to guide it. Notice the pause at the top of an inhale and the longer, looser release that follows. Each exhale can travel a little further than the last, like a tide drawing back from shore. There is nowhere this breath needs to reach, just the rise, and the fall, and the rise again, carrying you a little further from waking. At the very center of a black hole lies the singularity, a theoretical point where density becomes infinite. Here, the equations of general relativity stop making sense, breaking down entirely. Physicists describe it less as a place and more as a boundary of our understanding. What truly happens there, hidden from any outside view, remains one of physics' deepest open questions. Time itself behaves strangely near a black hole's edge. As gravity intensifies close to the event horizon, clocks there tick slower compared to those far away. A distant observer watching someone approach the horizon would see their movement stretch out, freezing at the boundary forever. For the traveler themselves, nothing would feel unusual at all, just steady moments passing. In 2015, gravitational waves were detected for the first time, ripples in space itself born from two colliding black holes. Instruments called LIGO measured a distortion smaller than the width of an atomic nucleus. The signal had traveled for over 1 billion years before reaching Earth. It confirmed a prediction Einstein had made a century earlier, one he himself once doubted could ever be observed. Distant stars sometimes reveal a black hole's presence simply by how they move. Instead of orbiting nothing, they trace wide arcs around an invisible point, tugged by gravity from something unseen. By tracking these orbits carefully over years, astronomers can calculate the mass hiding at the center. This is how many black holes are found, not by sight, but by their quiet influence on their neighbors. Matter spiraling toward a black hole rarely falls straight in. Instead, it gathers into a flattened, glowing accretion disk, circling faster and faster as it nears the center. Gas, dust, and stellar debris collide and compress within this swirling structure. The disk itself becomes one of the brightest things in its region of the galaxy, lit by its own violent motion. Inside that spiraling disk, friction and compression generate extraordinary heat, reaching millions of degrees. Particles collide at tremendous speeds, releasing energy across the entire spectrum of light. The innermost regions glow far brighter than any star, radiating heat that would vaporize almost anything nearby. Yet from a safe distance, all of this appears as a soft, steady glow. Telescopes tuned to X-ray light are how many black holes are found at all. The scorching inner disk emits radiation far beyond what human eyes could ever perceive. Orbiting observatories capture this X-ray glow, translating it into images astronomers can study. Without this invisible light, countless black holes scattered across the galaxy would remain completely hidden from view. Narrow jets of particles sometimes erupt from a black hole's poles. These streams launch outward at speeds approaching the speed of light, stretching for thousands of light-years across the surrounding galaxy. They form where twisted magnetic fields channel energy away from the swirling disk below. Seen from afar, a jet can outshine the galaxy that hosts it, a beam of light older than any star in its path. In the 1960s, a physicist named Roger Penrose imagined a way to draw energy out of a spinning black hole. He proposed that an object could split in two near the black hole's rotating space, with one piece falling in while the other escapes carrying away more energy than it started with. The black hole's own spin would supply the difference. It was a theoretical proof that even black holes are not entirely closed systems. Around every rotating black hole lies a region called the ergosphere. Here, space itself is dragged along by the black hole's spin, forced to move in the same direction, no matter what an object tries to do. Nothing can hold still inside this zone, not even light. Yet, unlike the event horizon, the ergosphere still allows escape, making it a place where energy can be borrowed rather than lost forever. Let the weight of this moment settle into you now. Feel your shoulders sink a little further into whatever is holding you, heavier than they were a few minutes ago. Let your arms rest, unlifted, unneeded, simply resting where they lie. Your legs grow heavy too, sinking down as if the mattress were slowly rising up to meet them. There is nowhere for that heaviness to go but down, and down is exactly where it belongs tonight. An object crossing into the ergosphere can leave richer than it arrived. This is the heart of the Penrose process, matter and radiation borrowing momentum from the black hole's own rotation. Each exchange nudges the black hole's spin down by the smallest fraction, a debt paid in slowing rotation. Multiply this effect across countless particles, and a civilization might one day harvest the spin of a black hole itself as fuel. In the 1970s, Stephen Hawking proposed something that surprised even those close to him. He suggested that black holes are not perfectly black at all, but instead emit a faint trickle of particles born from the strange rules of quantum physics at the very edge of the event horizon. Over immense stretches of time, this radiation would carry away mass and energy. Even the darkest object in the universe, it seems, slowly fades. Hawking radiation grows stronger as a black hole's mass grows smaller. A black hole the size of a galaxy's core radiates so faintly it is essentially undetectable, its glow lost against the cosmic background. But shrink that black hole down, and the radiation brightens, the temperature at its horizon climbing as the object itself shrinks. Mass and radiation move in opposite directions, one rising as the other falls. A small black hole disappears far sooner than a large one. Because its radiation burns brighter for its size, it loses mass more quickly, and that loss accelerates as it continues shrinking. The process feeds itself, growing faster the smaller the black hole becomes. A black hole, the mass of a mountain, could vanish within a fraction of a second under this quickening spiral. Entropy inside a black hole scales with the area of its event horizon, not its volume. This single relationship, uncovered through decades of theoretical work, hints that all the information a black hole ever swallowed might somehow be recorded across its surface rather than hidden within its depths. The idea remains startling even now, suggesting that three-dimensional space might, at its core, behave like a two-dimensional surface. A black hole no larger than a grain of sand would not last long at all. Its radiation would blaze so intensely that it could evaporate in a fraction of a second, releasing a burst of energy comparable to a large explosion. No such micro-black hole has ever been observed, but the mathematics describing its fate remains as precise as anything else in this science of shrinking, radiating darkness. No spacecraft, probe, or instrument built by human hands has ever touched or captured a black hole. Every image, every measurement, every calculation comes from studying its effects at a distance. We have watched stars swing around invisible companions and light bend around hidden mass. But the object itself remains beyond reach, known only through the shadow it casts on everything nearby. The closest black hole we know of sits more than 1,500 light-years from Earth. That distance is difficult to hold in the mind. Light leaving that region tonight would not reach us for over 1,000 years. Even our fastest spacecraft would take tens of millions of years to arrive. It remains, for now, a distant fact rather than a nearby neighbor. Darkness itself is why a black hole cannot be seen directly. It emits no light of its own, reflects none, and swallows whatever falls across its edge. Telescopes searching for one are really searching for absence, a place where stars vanish or bend unexpectedly. The black hole hides behind the very brightness of everything around it. A network of telescopes spanning the entire Earth once worked together to trace the outline of a black hole's shadow. Linked across continents, their combined signals formed something like a planet-sized eye. What emerged was a glowing ring surrounding utter darkness, the first true portrait of an event horizon's edge. That image traveled to screens everywhere, calm and orange against the black. Somewhere beyond the window, a low hum drifts in and fades, like a house settling into the night. It rises without hurry, holds for a moment, and lets go again. There is no need to follow it anywhere. Let your shoulders sink a little further into the mattress, heavier than before. The hum returns once more, fainter this time, drawing further away with each breath you take. To leave a black hole behind, an object would need to travel faster than light itself. That speed has never been reached by anything we know of, and physics suggests it never will be. This single threshold is what makes the boundary absolute. Cross it, and no signal, no particle, no whisper of information can find its way back out again. Around every black hole lies a boundary called the innermost stable circular orbit, the closest ring where matter can still travel safely without spiraling inward. Beyond that line, gravity overwhelms any stable path, and material begins its final descent. Inside this ring, physics allows no lingering, no calm circling. It marks the last quiet orbit before the pull becomes absolute. Near a small black hole, gravity does not pull evenly across an object's length. The near side is tugged far harder than the far side, stretching whatever approaches into a long, thin thread. Astrophysicists call this spaghettification, a vivid word for a violent stretching that would happen to anything drifting too close to a compact, small mass horizon. Massive black holes, despite their size, treat nearby matter far more gently than their smaller cousins. Because their horizons are so much larger, gravity changes more gradually across any given distance near the edge. An object could, in principle, cross the horizon of a truly supermassive black hole without feeling torn apart at all. Scale, it turns out, softens the encounter. An idea first imagined for capturing a star's entire output could, in theory, be reshaped around a black hole instead. Engineers of thought have long pictured vast structures encircling a source of energy, gathering its output rather than letting it scatter into space. Applied to a black hole, such a structure would face fiercer radiation, but the underlying principle stays the same: surround the source and collect what pours outward. Freeman Dyson, in 1960, imagined wrapping a star in a vast shell of collectors, catching every photon that would otherwise scatter into the dark. He called it, modestly, a thought experiment about civilizations far older than our own. Physicists still use his name for any structure built to harvest a star's full output. His question was simple: why let so much light go unused when it could power a whole society instead? Such a structure, if built around a black hole instead of a star, would face radiation far fiercer than any furnace of fusion. The inner layers would need to withstand X-rays, gamma rays, and particle storms streaming from the churn just beyond the horizon. Materials would have to shed heat faster than they absorbed it. Engineers of this hypothetical future would be designing not for comfort, but for survival at the edge of a maelstrom. Two physicists, Roger Blanford and Roman Znaják, described in 1977 a way to draw power directly from a black hole's magnetic field. Their process needs no direct contact with the horizon itself. Instead, twisted magnetic lines threading through the spinning space nearby can siphon energy outward, like a turbine turned by forces invisible to the eye. It remains one of the leading theories for how nature itself might already be lighting up distant jets. Magnetic fields, when anchored within the swirling disk of infalling gas, can reach down into the spinning space near a black hole and pull rotational energy outward. The disk acts almost like a loom, weaving field lines that twist tighter with every orbit. Energy drawn this way does not come from the matter falling in, but from the black hole's own spin. It is a subtle exchange, gravity and magnetism trading power across the boundary of the unseen. A black hole's rotational energy, locked into the fabric of spacetime itself, could in theory be converted into usable power for whoever learned to reach it. The spin is real, measurable, immense, a store of motion built up over the collapse and growth of a dying star. No engine on Earth resembles what would be needed to tap it, yet the physics allows the possibility, however distant such an engine remains from any workshop we know. Let warmth begin somewhere small, the center of your chest, a low and steady glow. Let it spread outward, unhurried, into your shoulders, down through your arms, into your fingertips resting still. Feel it settle into your hips, your knees, the long muscles of your legs, each place growing heavier as the warmth arrives. There is only this slow spreading, this body finding its own low, even heat, drifting further into rest with every breath. Drawing rotational energy from a black hole does not come without cost. Every joule extracted through magnetic fields or twisted spacetime slows the spin by some small, immeasurable fraction. Over long enough stretches of time, a black hole harvested this way would wind down, its horizon settling into a slower turn. Nothing in physics offers a free exchange. Even the darkest object in the universe pays a price for the energy it gives. Feeding matter into a black hole releases energy on a scale nuclear reactions cannot approach. As gas, dust, or debris spirals inward, friction and gravity heat it to temperatures beyond any furnace, radiating light across the spectrum before it ever crosses the horizon. This glow is what allows astronomers to see black holes at all, despite their darkness. The infall itself becomes the brightest event for light years around. Matter falling into a black hole can convert up to 42% of its own mass directly into energy before it disappears past the horizon. That number, drawn from the physics of rotating black holes, dwarfs anything else known in nature. Almost half of what falls in simply becomes light and heat, radiated outward for any watching eye to see. It is one of the most efficient transformations the universe permits. This efficiency far outpaces nuclear fusion, the very process that powers every star in the sky. Fusion converts only a sliver of mass into energy, a fraction of a single percent, even in the fiery heart of the sun. A black hole, by contrast, could turn matter into energy dozens of times more effectively without needing the delicate balance fusion demands. It is, by the numbers alone, the most potent furnace physics allows. Fusion, the fire that powers every star, converts less than 1% of its mass into energy. Even in the sun's crushing core, where hydrogen fuses into helium under immense pressure, most of the original mass simply remains matter, unchanged and unreleased. This is why stars burn for billions of years, rather than vanishing in an instant. It is an efficient process by ordinary standards, yet almost wasteful compared to what a black hole allows. A civilization far beyond our own might treat a black hole not as a hazard, but as a converter, a device for turning raw matter directly into energy. Feed it rock, gas, or discarded metal, and the black hole would return light and heat in staggering proportions. No moving parts, no fuel rods, no reactor core to maintain. Just gravity itself doing the work, patiently and without complaint. Feeding a black hole in careful measured amounts could act as a kind of throttle. Too little matter, and the output dims. Too much, and the accretion disk grows unstable, flaring unpredictably. A civilization harvesting such energy would need to regulate the stream precisely, like tending a fire that never quite goes out, but must never rage out of control either. A stable ring of collector satellites, orbiting at a safe distance, could gather the radiation pouring outward from an accretion disk. Positioned just beyond the fiercest heat, each satellite would intercept a slice of the glow, converting it into usable power. Spread across a wide orbit, thousands of such collectors might work in quiet unison, drawing energy from light that would otherwise scatter uselessly into the dark. Thin sails, built like solar sails but tuned to X-rays, could catch the fierce light shed by matter falling inward. Where ordinary solar panels absorb visible light, these would need coatings capable of surviving radiation far more punishing than sunlight. Angled carefully, they might drift on the pressure of that light alone, gathering energy while barely needing to move. An engine built this way might rival the efficiency of matter, antimatter reactors, a technology that so far exists only on paper. Both processes promise to convert mass almost entirely into usable energy, far beyond anything chemical or nuclear fuels allow. A black hole, unlike antimatter, requires no exotic material to manufacture. It is simply there, waiting, offering its gravity as the engine of transformation. Somewhere behind closed eyes, a thin trail of dust drifts through a shaft of still air, catching a single ray of light before settling again. There is no rush in its falling, no destination it must reach. It simply moves the way breath moves, rising and lowering without effort. Let your own weight follow that same unhurried descent, sinking a little further into the mattress with each slow moment. Nothing here needs finishing tonight. Antimatter annihilation remains the only other known process with comparable efficiency, converting mass into energy at rates fusion cannot match. When matter meets its antimatter twin, both vanish completely, releasing pure energy in an instant. The trouble is manufacture. Antimatter is fantastically rare and costly to produce. A black hole demands no such creation. It works with whatever ordinary matter happens to fall its way. In 1960, a physicist named Freeman Dyson considered whether a black hole might one day serve as an engine for propulsion. Long before black holes were confirmed by observation, Dyson imagined civilizations using their gravity and radiation to move enormous structures through space. His thinking treated the darkest objects in the cosmos as tools rather than mysteries, a habit of mind that still shapes speculation about advanced engineering today. A concept known as the black hole bomb theorizes that waves trapped near a rotating black hole could be amplified again and again. Under the right conditions, a wave bouncing between a mirror and the black hole's ergosphere would grow stronger with each pass, drawing energy from the hole's spin. It remains a mathematical curiosity, untested by experiment, yet it hints at how strange and generous a spinning black hole's physics can be. Superradiance describes how waves passing near a rotating black hole can leave with more energy than they arrived carrying. A wave that grazes the ergosphere borrows a portion of the hole's spin before continuing outward, larger than before. This works for light, for radio signals, even for gravitational waves themselves. Physicists first outlined the mathematics in the 1970s, describing rotation as a hidden reservoir waiting to be tapped. Such wave scattering, if harnessed deliberately, could theoretically boost the total energy drawn from a spinning black hole, far beyond what ordinary accretion provides. Each pass through the ergosphere adds a small increment, and with enough repetitions the total could grow enormous. Engineering such a system remains entirely theoretical. No civilization has attempted anything resembling it. Yet the physics offers no obvious ceiling to how far the amplification might extend. Transporting a black hole would first require overcoming its own gravity, a force that dominates everything nearby. Even a modest stellar mass black hole holds enough pull to bend the paths of stars from vast distances. Moving it even slightly would mean countering that pull directly, without anything solid to push against. No known method exists for applying such force at this scale. A black hole could, in principle, be towed using something called a gravitational tractor. Rather than touching the object at all, a nearby spacecraft would draw the black hole along using nothing but its own mass, the way two bodies drift toward each other under gravity. The method has been proposed for redirecting asteroids. Applying it to a black hole would demand a tractor almost unimaginably massive. This method relies on the spacecraft's own gravity, pulling its target forward without any contact at all. The spacecraft hovers near its target, and the pull between the two masses draws them together across long stretches of time. For an asteroid, a craft the size of a small vehicle might suffice. For a black hole, the tractor itself would need to rival a planet in mass. Moving a stellar mass black hole would require energy far beyond anything human civilization currently produces. Its mass alone rivals several suns compressed into a single point, and shifting that mass even a short distance demands staggering amounts of work. Present-day rockets and reactors fall short by many orders of magnitude. The gap between ambition and capability here spans centuries, if not far longer. Creating an artificial micro-black hole has never been achieved, despite decades of theoretical interest. The idea requires compressing matter into a space smaller than its natural size allows, concentrating enough mass or energy that gravity finally overwhelms every other force. Laboratories on Earth remain far too limited in scale for such a feat. Even the largest particle accelerators fall short by many magnitudes. Let the jaw loosen, just slightly, the way it does in the deepest part of sleep. Feel the small muscles around the eyes release whatever tension had gathered there through the day. Behind closed lids, there is only a dim, private dark, wide enough to hold whatever drifts through it. Let your face rest the way still water rests, without needing to hold any particular expression at all. The night asks nothing further of you. Cosmic ray collisions, which strike Earth's atmosphere with tremendous natural force, have also failed to produce any observable micro-black holes. Physicists once wondered whether high-energy particle accelerators might create them briefly, vanishing almost as soon as they form. Years of careful searching turned up no trace. The absence itself has become useful, narrowing which theories about extra dimensions and hidden energy scales remain viable. Certain theoretical models propose that micro-black holes, if they could be stabilized, might serve as compact and long-lived power sources. Rather than evaporating in an instant, a carefully balanced micro-black hole could, in principle, persist for extended periods while radiating usable energy. The idea remains speculative, resting on physics no experiment has yet confirmed. Even so, it captures the imagination, a reactor no larger than a coin, drawing power from a hole the size of a proton. Feeding must never stop if a stabilized micro-black hole is to remain useful. Left alone, even a carefully balanced one would slowly bleed away through Hawking radiation, shrinking toward nothing. A steady trickle of matter, added with precision, could offset that loss. The reactor would become less like a furnace and more like a small, hungry mouth that must always be given something to hold its shape. Hawking radiation from a small black hole could itself be harvested as energy, turning apparent loss into gain. As the hole radiates particles outward, collectors positioned nearby could absorb that faint glow and convert it into usable power. The smaller the hole, the brighter this radiation becomes. In principle, a reactor could run on the very process that would otherwise cause it to fade away. Inside a spacecraft, a micro-black hole reactor could theoretically fit within a space no larger than a household furnace. Its mass might rival a mountain, yet its physical size would remain smaller than a proton. Such compactness is part of its appeal. Enormous energy density, folded into almost no volume at all, tucked quietly behind reinforced walls. Magnetic or gravitational confinement would be required to hold a micro-black hole in place, keeping it from drifting toward the walls of its container. Charged particle traps, shaped by powerful magnetic fields, might suspend it in a stable pocket of space. Gravitational balancing, using surrounding mass, offers another theoretical approach. Either method demands precision measured in fractions of a hair's width. Losing containment of a micro-black hole could be catastrophic, at least in theory. If the confining fields failed even briefly, the hole might sink through the floor of its housing, drawn by ordinary gravity toward the densest matter nearby. Engineers who study the concept treat containment failure as the defining risk of the entire design, worth guarding against above all else. A runaway micro-black hole could, in theory, consume surrounding matter without limit, growing slowly heavier as it fell through whatever lay in its path. Deep within a planet, it might sink toward the core, drawing in rock and metal along the way. The pace of such consumption remains uncertain, and estimates vary widely, but the scenario itself has kept containment engineers thoughtful and careful. Some models suggest micro-black holes might pass through ordinary matter almost harmlessly, their cross-section so small that they rarely strike another particle directly. Under this view, a stray micro-black hole could pass through a planet the way a needle passes through empty air, doing little damage along the way. The physics remains unsettled, but the possibility offers a quieter alternative to the runaway scenario. Physicists debate whether stable micro-black holes could exist at all, given how thoroughly quantum gravity remains unresolved. Some frameworks permit them under specific, exotic conditions. Others rule them out entirely. No experiment has settled the question either way. The debate itself reveals how much of this reactor concept rests on physics still waiting to be discovered, tested, or disproven. Notice the air moving in, and then the longer, slower path it takes moving out. There is no need to shape the breath into anything particular. Let each exhale run a little further than the one before, unwinding like a thread let loose from its spool. With every release, the shoulders drop a fraction more, and the mind follows the body downward into rest. A Kardashev Type II civilization could theoretically harness the entire output of its home star, capturing nearly every particle of light it produces. This would dwarf anything humanity currently draws from the sun, which uses only a sliver of the light that reaches Earth. Such a civilization would measure its wealth not in resources mined from the ground, but in starlight fully claimed. To harvest a black hole at all, a civilization would already have moved past what theorists call Kardashev Type II, the stage of claiming an entire star's output. Drawing usable power from a collapsed star's gravity well demands tools and reach that dwarf anything a single solar system could provide. The scale involved points toward a builder whose ambitions and instruments span far beyond one sun. A Kardashev Type III civilization is imagined as one that draws its energy from an entire galaxy, not merely a single star. Its reach would extend across billions of suns, threading collectors and conduits through spiral arms and dust lanes alike. Such a society would treat a galaxy's light the way a household treats a lamp, switched on and drawn from without a second thought. The idea remains a framework for measuring ambition, not a confirmed destination. A civilization capable of drawing power directly from a black hole might be placed even further along this scale, sometimes called Kardashev Type IV. At that level, energy would no longer come from stars at all, but from the raw gravitational and rotational reserves locked inside collapsed matter. It is a category built entirely from extrapolation, a rung on a ladder no one has yet climbed. Certain theorists have proposed that black holes might serve as the ultimate long-term energy source, outlasting every star that ever burned. Where a sun eventually exhausts its fuel and fades, a black hole's mass remains bound within its horizon, patient and largely undiminished. The proposal treats collapsed stars not as endings, but as extraordinarily durable reservoirs waiting to be tapped. Every star eventually burns out, its fusion fires dimming as fuel runs thin across billions of years. A black hole, by contrast, could theoretically go on providing energy long after the last star has gone dark. Its power comes not from burning fuel, but from gravity and rotation, resources that fade far more slowly. In this sense, a collapsed star might outlive the very light that once formed it. A black hole's reservoir of usable energy could, in principle, stretch across timescales that no ordinary star could ever match. Where a sun's fusion clock runs for mere billions of years, a black hole's mass and spin persist for spans that make stellar lifetimes look brief. The comparison is less about immediate power and more about endurance, the quiet advantage of something built to last. Engineers imagining a structure built around a black hole to gather its radiated energy give it a name borrowed from an older idea, the black hole Dyson sphere. Instead of surrounding a star, the shell would encircle a collapsed one, catching X-rays and particle streams instead of ordinary sunlight. The concept keeps the same architecture, only aimed at a darker, denser kind of light source. Such a structure would not sit close against the black hole's edge, but would orbit well beyond the event horizon, at a distance chosen for safety and stability. Positioned there, it could gather radiation streaming outward from the accretion disk without straying into the steep gravitational slope nearer the center. Distance, in this design, becomes as important as the collectors themselves. Any structure built to gather energy this close to a black hole would need shielding far beyond anything used around an ordinary star. Radiation pouring from the accretion disk includes X-rays and high-energy particles capable of tearing through conventional materials in moments. Engineers imagining such collectors describe layers of exotic, radiation-hardened material simply to keep the structure intact long enough to function. Let the weight of the body settle now, beginning wherever it rests heaviest. Feel the head grow heavy against the pillow, sinking a little deeper with each passing moment. Let that heaviness travel down through the neck, into the shoulders, spreading like warmth through tired muscle. Let the arms grow heavy, then the chest, then the hips, each part settling further into the mattress below. Let the legs go last, heavy from hip to heel, the whole body resting, unmoving, held entirely by what lies beneath it. Picture a wide circle of small satellites positioned around a black hole, each one nudging loose gas inward along a careful path. Rather than dumping matter all at once, the ring could release it in measured streams, keeping the flow steady and predictable. This kind of controlled feeding would let engineers regulate exactly how much material enters the black hole, and therefore how much energy comes back out. Decades before black hole engineering entered serious discussion, physicist Leonid Shkadov proposed a different kind of megastructure. His idea involved a giant mirror positioned near a star, reflecting radiation asymmetrically so the imbalance produced thrust. Over vast stretches of time, that gentle push could shift the star's position, dragging along everything gravitationally bound to it, including entire planetary systems. The same logic behind a stellar mirror has been extended, at least on paper, to black holes themselves. Instead of reflecting starlight, a structure could intercept and redirect the narrow jet firing from a black hole's pole. If shaped correctly, that redirected stream would push back against the structure, turning raw jet energy into directional thrust for the entire system attached to it. Individual, relativistic jets already travel outward at speeds approaching that of light, carrying enormous momentum with them. Engineers imagining interstellar travel have proposed capturing a fraction of that momentum through a shaped reflector trailing behind a spacecraft. In theory, no fuel would need to be carried at all. The black hole itself would supply the push, jet after jet, across unimaginable distances. A more exotic proposal skips jets altogether and turns to the faint trickle of Hawking radiation itself. A small black hole held near a spacecraft would radiate particles asymmetrically if shaped correctly, producing a slow but steady thrust. No propellant would be spent, since the black hole's own mass slowly converts into the radiation, pushing the ship forward. This idea was formally proposed by physicist Lewis Crane in 2009 in a paper describing what became known as a black hole starship. Crane calculated how a sufficiently small black hole might be created and then shaped to emit Hawking radiation directionally. His paper treated the concept seriously, even while acknowledging that the technology required lay far beyond anything achievable today. Beyond propulsion, a black hole engine offers something more fundamental, a way of converting almost any form of matter into pure usable energy. Waste, debris, or exhausted materials could, in principle, be fed into the black hole and returned as radiated power. Nothing would need sorting or refining first. The black hole would simply accept mass and release energy in return. For any civilization managing enormous quantities of discarded material, this offers an elegant kind of closure. Rather than storing waste indefinitely or scattering it into space, it could be directed toward a black hole and transformed entirely. What enters as clutter and residue would emerge as radiated light, closing the loop between disposal and power generation in a single continuous process. Such a disposal system could not simply release matter and hope for the best. Every parcel of waste would need a precisely calculated trajectory, timed and angled to enter the accretion disk without overwhelming it. Too much material arriving too quickly could saturate the system, so navigation near the black hole would demand a level of precision far beyond ordinary spaceflight. If too much matter arrived at once, the accretion disk itself could become unstable, its temperature and radiation output swinging unpredictably rather than settling into a steady glow. Instead of a reliable stream of energy, an overfed black hole might flare violently before quieting again. For a system built on steady power, that kind of instability would defeat the entire purpose of harvesting it. Beyond the window, a low hum rises and fades, the sound of a house settling into itself. Somewhere a pipe ticks, then goes still. Wind brushes the eaves and moves on, leaving no trace behind. There is no need to place it, no need to name it. Just let it arrive, and let it leave, the way breath arrives and leaves without asking anything of you at all. Across a hypothetical solar system, a civilization might send fleets of small vessels out to mine asteroids purely to feed a black hole reactor. Rock and metal, stripped from drifting bodies, would become raw fuel rather than construction material. Instead of building ships or habitats, the harvested stone would be aimed inward, toward the glowing throat of an accretion disk, its only purpose to burn. Each mined asteroid could supply a dependable trickle of feedstock, arriving in measured amounts rather than sudden bursts. Steady input matters more than raw quantity, since a black hole engine thrives on consistency. A slow, continuous stream of dust and rubble spread evenly over the disk would keep the light output even, avoiding the flares that come from feeding too much at once. A black hole power station might orbit at only a fraction of a light year from its source, close enough to gather energy efficiently, far enough to remain untouched by its violence. At that distance, the black hole would appear as a small, intensely bright point, its accretion disk outshining any star nearby. Structures orbiting there would live permanently inside its glow. Holding a stable orbit that close to a black hole is nothing like orbiting an ordinary star. Space itself curves so sharply nearby that ordinary orbital mechanics no longer apply. Engineers would need relativistic corrections built into every calculation, accounting for how gravity bends paths and how velocities near such intensity behave in ways Newton's equations were never meant to describe. Messages sent near a black hole would not arrive at the same rate they were sent, because time itself runs differently there. A signal broadcast from close to the horizon would stretch and slow before reaching distant listeners, arriving later and lower in pitch than intended. Communication would no longer be instantaneous, even by the loose standards of interstellar distance. Engineers stationed in orbit near the black hole would age differently than colleagues watching from farther away. A single day for them might correspond to weeks or months elsewhere, depending on how close they orbited. Returning from such a post would mean stepping back into a future already shaped by decisions and events they had missed entirely. Physicist Carl Schwarzschild, writing in 1916, found the exact mathematics describing this warping of time and space around a single massive point. His solution, now called the Schwarzschild metric, remains the foundation for understanding how gravity bends time near a black hole. It was derived from Einstein's equations within months of their publication, a rare case of theory arriving almost as fast as the idea itself. Overhead, orbiting satellites already prove this effect every day, far from any black hole. GPA's satellites experience time slightly differently than clocks on Earth's surface, and their systems must correct for it constantly to keep navigation accurate. The correction is tiny, measured in millionths of a second. Yet without it, positioning errors would accumulate into kilometers within hours. A civilization capable of harvesting black holes might turn this same effect into a tool for storage rather than travel. Data placed on a probe orbiting close to the horizon would age far more slowly than data kept elsewhere, effectively preserving it across vast stretches of outside time. In this sense, proximity to a black hole could function as a kind of vault, holding information nearly frozen while centuries pass beyond it. Extreme time dilation carries a strange possibility. A civilization stationed near a black hole's edge could let vast spans of external time pass while barely aging at all. A crew might spend a single year in close orbit and return to find centuries had unfolded elsewhere. In effect, the black hole becomes a bridge across history, letting those nearby arrive at a distant future without ever measuring the years themselves. Let warmth begin at your feet, spreading upward like sunlight moving through still water. Feel it reach your ankles, then your knees, loosening whatever tension the day left behind. Let it rise into your chest, unhurried, filling the space behind your ribs with a low, steady glow. Let it climb into your shoulders, down through your arms, into your fingertips, until every part of you rests in the same tender warmth, heavy and unbothered by time. Traveling forward in time, in a literal sense, becomes almost imaginable once this stretching is taken seriously. A harvested black hole might serve less as a fuel source and more as a doorway, letting travelers step briefly close to its gravity and emerge years or decades ahead of everyone they left behind. It would not be travel through time so much as travel through distance from it. Probes sent on close, fast orbits around a black hole could return, having aged far less than the instruments and observers who stayed behind. A short journey near the horizon might correspond to years passing across the wider galaxy. Engineers, watching from a safe distance, would essentially be waiting for messages from their own future, delivered by machines that experienced almost none of the intervening time themselves. An elevator, at least as a concept, could lower material toward a black hole's pull and lift it away again before it ever crossed the horizon. Each cycle would draw energy from the descent and release it on the way back out, over and over, without consuming the black hole itself. It is less a mine than a rhythm, matter swinging inward and outward, like a slow mechanical breath. Satellites built to survive such conditions exist only in sketches and equations for now. Engineers imagine shells woven from materials that shrug off radiation fierce enough to strip ordinary metal to its atoms. These exotic surfaces would need to endure heat, particle bombardment, and gravitational strain all at once, conditions no laboratory on Earth has ever needed to test. Negative energy density describes a form of matter that would push against gravity rather than yield to it, and no experiment has ever produced or confirmed it. It appears in equations as something mathematically permitted, a kind of shadow substance that balances certain physics on paper. Whether nature allows it to exist in any form remains an open question. One physics has not yet answered either way. Certain propulsion concepts, the kind that promise faster travel through warp space, depend entirely on this same unconfirmed matter to function. Without it, the mathematics collapses back into the ordinary limits of rockets and fuel. Engineers who study these designs treat them as elegant possibilities rather than blueprints, waiting on a discovery that may never arrive. Light bending around a harvested black hole could, in theory, be shaped into a lens far larger and stranger than anything built by hand. Its gravity would curve passing light the way glass curves a beam, magnifying whatever lies far beyond it. A civilization stationed nearby might use this natural distortion as an instrument, turning gravity itself into a kind of telescope. Magnified by this bending of light, distant galaxies could appear closer and clearer than their true distance would ever allow through ordinary observation. Structures invisible to conventional telescopes might resolve into detail, borrowed entirely from the black hole's own gravity. It would be a strange kind of sight, seeing the universe not through glass or mirrors, but through the curvature of space itself. A megastructure encircling a black hole could turn its gravitational lensing into more than a lens for watching distant galaxies. Bent starlight, focused with enough precision, might carry signals across vast distances the way a curved mirror redirects a beam. Engineers imagining such a relay picture messages riding on light, already warped by gravity, reaching listening posts, scattered far beyond ordinary reach. It remains an elegant thought experiment, nothing built, only sketched. Certain equations describing black holes hint at tunnels connecting one region of spacetime to another, structures physicists call wormholes. The mathematics allows for them the way a folded sheet of paper allows two distant points to touch. Whether such folding happens anywhere in the real universe is another matter entirely. The idea persists mostly on chalkboards, admired more than confirmed. Somewhere far off, an ember rests in a dish of ash, its glow fading by degrees. No one is watching for. There is no hurry in the way it dims, no moment where it decides to let go. It simply cools, the way a held breath eventually softens into ordinary breathing. Let your body follow that same unhurried fading. No effort required, no destination waiting. Wormholes have never been observed by any telescope, detected by any instrument, or confirmed by any experiment. They live inside the mathematics of general relativity, permitted by the equations but unseen in the sky. Physics has produced no image, no signal, no trace, suggesting one exists anywhere. For now, they remain a possibility written in symbols, not a discovery written in light. Einstein and a colleague named Rosen once described a bridge joining two separate regions of spacetime through the throat of a black hole's mathematics. Their solution, published in the 1930s, showed the equations technically allowed such a passage. It was never meant as a travel route, only a curious feature buried inside the geometry. The bridge remains theoretical, admired for its elegance rather than its practicality. No physicist has ever demonstrated a wormhole stable enough or wide enough for anything to pass through and survive. Every known solution collapses almost instantly, sealing shut faster than light could cross it. Keeping one open would require matter with properties nothing in nature has shown to exist. The bridge stays closed in every version physics can currently support. Some physicists speculate that the crushed core of a black hole, rather than ending in nothing, might bounce outward into an entirely new universe on the other side. In this picture, our own cosmos could have begun the same way, born from the collapse of matter inside some earlier black hole. No observation supports it, and none contradicts it either. It remains a quiet, unproven possibility. Maybe universes forming inside black holes belong to the realm of speculation, a mathematical curiosity without evidence to anchor it. The idea appears in certain theoretical models of quantum gravity, models still searching for confirmation of any kind. No signal has ever reached us from such a newborn cosmos, nor could one if the theory holds. It stays a poetic possibility, nothing more. A puzzle known as the information paradox asks a simple question with no simple answer. What becomes of everything that falls past a black hole's horizon? Quantum theory insists information can never truly vanish, yet general relativity seems to erase it completely inside the singularity. The two great theories disagree, and neither yields. Physicists have wrestled with this contradiction for decades. The information paradox remains unresolved, one of the deepest open questions in theoretical physics today. Proposed solutions range from radiation encoding hidden details to entirely new geometries near the horizon, yet none has settled the debate. Every attempt reshapes the puzzle rather than closing it. The answer, whatever it turns out to be, likely waits somewhere still beyond current understanding. Whatever finally resolves the information paradox may carry consequences far beyond philosophy. A deeper understanding of how a black hole handles matter and energy could reshape the physics of extraction itself. New equations might reveal efficiencies no one has yet imagined, or limits no one has yet respected. The puzzle, once solved, might quietly rewrite the rulebook for harvesting. Certain theorists have floated the idea that black holes might serve as thresholds into other regions of spacetime entirely. In this framework, the singularity is not an ending but a seam, stitching our universe to another fold of reality. No mathematics fully confirms this, and no observation denies it. It remains an elegant, open thought experiment. Multiverse theories, still speculative at their edges, imagine that energy itself might slip between neighboring universes through black holes. If true, a harvested black hole could act less like a battery and more like a doorway, leaking power to places we could never observe. The evidence for this stays thin, almost non-existent. Still, the thought lingers in certain corners of theoretical physics. Let your jaw loosen now, just slightly, the way it does in the deepest part of sleep. Feel the small muscles around your eyes give up their hold, lids growing heavier with each breath. There is no expression to keep, no face to hold in place. Let it soften into stillness like a lake losing its ripples. Whatever is behind your closed eyes can simply rest there, unwatched, unhurried, safe in the dark. A civilization advanced enough to tend a black hole might use its power for engineering on a planetary scale, reshaping continents, redirecting weather, or lifting entire cities into orbit could all draw from such a reservoir. The energy needed for such feats dwarfs anything modern industry commands. It would take a species that treats stars, not rivers, as its power source. Stellar engines, imagined decades ago by physicists sketching far future technology, propose using directed thrust to move an entire star system through space. Swap a star's radiation for a black hole's jet, and the concept scales upward dramatically. Entire solar systems could drift, slowly steered like ships on a vast, dark sea. It stays theoretical, but the mathematics of motion holds steady. Steering a star with a black hole's thrust could, in principle, let a civilization dodge dangers drifting through the galaxy. A wandering rogue star, a stray cloud of gas, even the slow gravitational pull of a passing cluster might all be avoided with patient course correction. The scale is staggering, yet the physics permits it. Nudging a sun is not impossible, only unimaginably slow. Escaping a galaxy destined for collision is one of the more sobering reasons a civilization might turn to such propulsion. If home becomes unstable, a black hole engine offers a way to relocate an entire star system elsewhere. It is survival measured across eons, not lifetimes. The idea sits at the edge of speculation, tethered loosely to real orbital mechanics. Andromeda and the Milky Way are moving toward each other, drawn by mutual gravity across an immense span of space. Astronomers estimate their merger will unfold roughly 4.5 billion years from now. Neither galaxy will end in a single dramatic instant. Instead, they will slowly interweave, stars sliding past each other in a graceful cosmic drift. When galaxies merge, gravitational tides can pull stars from their gentle, familiar orbits into new and unfamiliar paths. Planets once nestled safely around a stable sun might find their star nudged, tilted, or torn away entirely. Habitability, fragile even under calm conditions, could unravel over these long transitions. It is less an explosion than a slow reshuffling of cosmic furniture. An Exodus fleet powered by a captured black hole is a purely speculative survival scenario, something imagined rather than engineered. No civilization has built one, and no blueprint exists beyond thought experiments. The idea simply asks what desperation might inspire, given enough time and enough physics. It belongs to the realm of possibility, not present fact, a story told to test the limits of imagination. Beyond fleeing danger, other thinkers wonder whether an advanced civilization might choose to build a black hole on purpose. Rather than searching the cosmos for one, they would manufacture their own, tailored to a specific need. It is an idea born from extrapolation, not evidence. No technology known today could achieve it, yet the thought lingers at the edge of theoretical engineering. Making an artificial black hole would require compressing matter far beyond anything current technology allows. Densities needed exceed what any particle accelerator or laser array on Earth can produce. Matter would have to be squeezed into a space smaller than an atom's nucleus, packed until gravity itself takes over. The physics is understood in principle. The means remain entirely out of reach. One speculative design imagines vast arrays of lasers converging on a single point, compressing matter until it collapses under its own gravity. Each beam would add pressure, layer upon layer, until density crossed an invisible threshold. The resulting collapse would, in theory, birth a black hole from nothing but focused light and matter. It remains an idea sketched in equations, not yet tested in any physical form. Let your breath lengthen now, just a little more, with every exhale. Notice how the air leaves you without effort, the way a tide withdraws from shore. There is no need to guide it. It knows its own rhythm, has always known it, long before thought arrived. Let each breath grow longer than the last, each pause a little deeper, each return a little slower to arrive. Theoretical physics gives a name to a black hole formed purely from concentrated energy, a Kugelblitz. Unlike ordinary black holes born from collapsing stars, this one would emerge from light and radiation alone, gathered so densely that space itself would curve and close around it. The concept follows directly from Einstein's equations, where energy and mass are simply two faces of the same coin. No Kugelblitz has ever been observed, and none has ever been created in any laboratory on Earth. It exists only within calculations, a consequence of physics allowed but never realized. The energy required to form even a tiny one would dwarf anything humanity has ever produced. For now, it remains a beautiful possibility written only in mathematics. Because a Kugelblitz forms without gathering physical mass, some imagine it as an almost perfectly clean energy source. Feed it light, and it might, in principle, return usable power through the radiation it eventually emits. No fuel, no waste, only energy transformed and returned. The vision is elegant. Whether it could ever be built remains entirely unknown. Speculative designs go further still, imagining reactors the size of cities built around a Kugelblitz core. Towers of collectors would ring the central point, drawing in radiated energy to power entire civilizations. Such structures exist only as concept art and thought experiments today. Yet the scale of ambition hints at how far imagination is willing to travel when energy becomes the only true currency of survival. Far ahead, long after every star has faded, a civilization might turn to black holes simply because nothing else remains. In a universe approaching heat death, when energy grows scarce and light grows rare, these dark objects could stand as the last reliable source of power. It is a distant, quiet thought, one that stretches imagination toward the very end of time itself. Heat death describes a theoretical state in which the universe reaches its maximum entropy, a condition where no more useful work can be done anywhere. Every form of energy would have spread out evenly, with nothing left concentrated enough to power motion or light. Physicists describe it as the end point of thermodynamic decay, not a violent ending, but a slow settling into uniform stillness. It is less an event than a horizon that time approaches without ever quite closing on. Across trillions of years, the stars themselves would have burned through every reserve of fuel they hold. Red dwarfs, the longest lived among them, might glow faintly for spans exceeding the universe's current age many times over. Eventually, even their embers cool, leaving galaxies scattered with dark, spent husks. No new light would rise to replace what fades. Black holes might be the last energy sources remaining in a heat-dead universe, long after every star has gone silent. Their gravity endures even when nuclear fires do not, and their slow radiance continues regardless of the darkness around them. In a cosmos stripped of starlight, these dim remnants could stand as the only structures still releasing anything at all. It is a strange kind of permanence, built from what light cannot escape. Evaporation time for a black hole scales with the cube of its mass, meaning size changes everything about how long one lasts. A small black hole might vanish within moments, while a stellar mass one could persist for spans far longer than the universe's present age. Triple a black hole's mass, and its lifetime does not triple in turn. It multiplies by many, many times over. Mass, in this sense, is destiny stretched across almost unimaginable time. The largest black holes could theoretically survive for a span called a googol years, a number written as one followed by 100 zeros. Supermassive giants, the kind found at the hearts of galaxies, would outlast nearly everything else in the observable cosmos. Their evaporation is so gradual that on any human timescale, they appear entirely unchanging. They are, in a sense, the last lights to dim in a universe already gone dark. For a few breaths, let your attention rest on the weight of your body against the mattress. Feel your shoulders sink first, then your arms, growing heavier with each breath. Your legs settle deeper still, ankles loosening, feet turning still and slack. Even your eyelids carry weight now, pressing downward, asking for nothing but rest. Let that heaviness spread through you, filling every limb until sleep gathers you in. A Google-year timescale vastly exceeds the current age of the universe, which itself is only about 13.8 billion years old. Written out, a Google looks like a 1 followed by 100 zeros, a number too vast for ordinary comparison. Against such a span, the entire history of stars, galaxies, and life so far amounts to barely a flicker. It is less a number than an invitation to feel how young everything still is. Harvesting the last black holes could represent civilization's final energy strategy, the last resource left when everything else has been spent. No stars remain to burn, no gas clouds to compress, no light to gather. Only these dim, patient remnants continue releasing anything at all. A civilization built to survive this era would have to learn to live on almost nothing, drawing warmth from what is essentially the universe's slowest exhale. In speculative writings about the far future, some describe what they call a dark era, a stretch of time when the only light left comes from evaporating black holes. A civilization here would gather around these fading points the way early humans once gathered around fire. There would be no stars overhead, no galaxies to chart, only scattered embers cooling across unimaginable distances. Existence, in this vision, becomes entirely about tending the last flames. Such a civilization would face energy that only diminishes, never renews. As each black hole it depends on slowly shrinks toward nothing. Every measure of power drawn from evaporation hastens the black hole's end, trading a little more darkness for a little more time. It is survival measured in ever-thinning returns, a slow negotiation between need and disappearance. Even the last light, in this telling, comes with an ending already written into it. Even the last black holes may not last forever. Physics suggests that, given enough time, every fragment of matter and every remaining black hole could dissolve into a thin mist of radiation, spread so evenly across space that nothing resembling a shape remains. No embers, no structure, only a faint hum of energy fading toward stillness. It would be the quietest possible ending, arriving without sound, without witness, and without protest. This diffuse glow, if it ever comes to pass, would mark the theoretical end of usable energy in the cosmos. Nothing left to burn, nothing left to fall, nothing left to convert. Physicists call this state maximum entropy, a condition where energy still exists but can no longer do anything at all. It is less an ending of matter than an ending of possibility, a universe complete but utterly unable to change. Within this long unfolding story, some physicists consider black hole harvesting the ultimate speculative frontier of engineering, a concept that sits at the very outer edge of what physics allows us to imagine. It borrows real principles, spin, radiation, gravity, and stretches them toward their furthest theoretical use. No blueprint exists, only equations and careful reasoning extended as far as they can go before certainty runs out. For now, the concept remains entirely theoretical, resting on mathematics rather than machinery. No spacecraft has approached a black hole, no structure has captured its radiation, and no civilization is known to have attempted it. Every description offered here belongs to thought, not to hardware. It is a rehearsal of ideas, waiting patiently for technology that does not yet exist and may never need to. In this way, black hole harvesting stands as a bridge, one end resting on confirmed physics, the other reaching into pure speculation. Event horizons, spin, and radiation are measured and real. Reactors, engines, and harvested starlight are imagined extensions built upon that foundation. The bridge itself may never be crossed, but it lets the mind walk from what is known toward what might one day be possible. In the end, harvesting a black hole remains one of the most extreme thought experiments in astrophysics, a way of testing how far imagination can travel while still holding a thread of real science. It asks what a civilization might become, and what the universe might still offer, long after stars have gone quiet. You have carried this thought gently tonight. Let it rest now, as you rest, unhurried, unfinished, and enough. Good night.